The data encrypted standard is giving us the same capability as the Enigma, but obviously its operation is different. And DES is our first modern cryptographic protocol. And this lecture is the big picture of DES, as well as how modern protocols give us encryption using just zeros and ones. So here's an example message or data set, and here we just have a text document, but the binary data behind it is now what our protocols are going to deal with. And so also with the Enigma, this was a typewriter. You would just type in the first letter, and then you'd enter the next letter, and you would just type in one letter at a time. But DES will take the binary data and it's going to break the message into 64-bit chunks. And this idea here is very common because computers can handle more than one item at a time. And now down to this last bit here at the bottom, this is also very common. It's called a padding. It's just an arbitrary add by the DES protocol, again called padding. So now we know that every single chunk that we send into the DES process is going to have a consistent and predictable bit length. So the message here is turned into a stack of these chunks. Each of these are going to be 64 bits. And then each chunk is going to go through the DES encryption process by itself and come out as a ciphertext or encrypted chunk. And our result is a stack of encrypted chunks, which together these constitute the ciphertext message. This whole stack is what Alice creates, and then Alice sends the whole stack to Bob. So this is so for DES, this is a somewhat confusing image. This is the defined DES protocol. And I'm showing you the same thing now, only now I'm showing it from left to right. I think it's a little bit easier to see. And we have the iterations again. These are just like the layers of our sandwich that we saw with Feistel. And for now, we're just going to cover this zigzag or this crossover that we see happening. And again, switching pictures again. This is Alice. Alice feeds her individual chunks into this process. The result of that is she gets her ciphertext, and then she sends Bob this ciphertext. And here is how the DES zigzag, or why we have it. So I'm just going to copy and paste this image, bring it over here, make it a little bit smaller. And now what I'm going to do now is I'm going to slowly make the mirror inverse of this image. And this is why we have the zigzag. So Alice sends Bob the ciphertext, and Bob is going to place it the reverse of the process, and because this design is the same forwards and backwards. And so also we see the number 8 or multiples of 8 is very common across software and hardware. And the DES also gives us lots of hardware efficiencies. So this is just an example. We've got 32 bits shown here. These 32 bits are going to run through this piece of hardware. Then they'll come out here. It'll get combined with the left column, and they're going to move over to this location. But at this point, DES is going to reuse this same piece of hardware, so it's efficient. You can think of it as the bits run through the piece of hardware, and then the design is such that it just routes them back to the start again. And back to mechanical cryptography, both parties had the same key, the shared secret key. This is our cipher or Caesar shift, and this is our secret shift. And then we have the Enigma secret settings. And there was also we had a known process that we went through that diffused and flattened patterns, which forced the impossible task for an attacker. So it was impossible for people to reverse engineer or logic attack, and it was impossible for a person to guess and check given the number of trials that they would have to do. So now modern cryptography now has large random numbers, and now we're in the world of computers, and all of these same characteristics apply. There's no patterns, and it's impervious to brute force. So the Enigma could bring in trillions of unique secret alphabets. But while doing so, the same inputs given the same secret every time will yield the same ciphertext. So the process is consistent. This process, given these two are the same, will repeat the same every time. And the same is true for modern cryptography. And here is something that seems a bit conflicting maybe at first. So our outputs act like a series of coin flips. These outputs are not predictable, or no patterns is not predictable in nature. However, this is also true. If you have the same inputs and the same secret, then there is predictability in your process. So these are opposite in concept, but both are also true here. And we'll be seeing a lot more of this as well.